Hello, my name is Jeremie Kim, and I'll be presenting our work, Revisiting RowHammer, an experimental analysis of modern devices and mitigation techniques. In order to access data from a DRAM row, say row 2, the memory controller must first open or activate the row. After all requests are serviced from row 2, the memory controller must close or precharge the row in order to begin accessing data from another row. Due to an increase in cell-to-cell interference as a likely result of increased cell packing density, rapidly activating and precharging a DRAM row can result in bit flips in nearby rows. Continuing to access the same row results in even more failures in nearby rows, and this phenomenon is known as RowHammer. We refer to the rapidly accessed row as an aggressor row, and the rows containing bit flips as victim rows. Denser DRAM chips are more vulnerable to RowHammer. 3 prior works provide RowHammer characterization data on real DRAM chips. However, there is no comprehensive experimental study that demonstrates how the RowHammer vulnerability scales across DRAM types and technology node generations and as DRAM chips become more dense. Therefore, it is hard to identify whether current mitigation mechanisms will remain viable for future DRAM chips that are likely to be more vulnerable to RowHammer. The goal of this work is to first experimentally demonstrate how vulnerable modern DRAM chips are to RowHammer and predict how this vulnerability will scale going forward. And second, we want to study the viability of current mitigation mechanisms on more vulnerable chips. We characterize over 1,500 DRAM chips from 300 DRAM modules, spanning the 3 major DRAM manufacturers, which we anonymize as A, B, and C, of 3 DRAM types or standards, DDR3, DDR4, and LPDDR4. We identified 2 technology nodes per DRAM type, old, new, 1X and 1Y, which we categorize based on manufacturing date, datasheet publication date, purchase date, and characterization results. From our experimental characterization, we make 3 key observations. First, chips of newer DRAM technology nodes are more vulnerable to RowHammer. Second, there are chips today whose weakest cells fail after only 4,800 hammers, or 4,800 accesses to 2 rows each. And third, chips of newer DRAM technology nodes can exhibit RowHammer bit flips in more rows and farther away from the victim row. We also evaluate the system performance impact when using different mitigation mechanisms on chips of varying degrees of vulnerability for 5 state-of-the-art mitigation mechanisms and 1 ideal refresh-based mitigation mechanism in green. We indicate with the orange vertical line the worst degree of RowHammer vulnerability that we observed across the modern DRAM chips that we characterized, and we find that available mitigation mechanisms can mitigate RowHammer in worse chips today with reasonable system performance overhead. However, we need a better solution for future DRAM chips that are likely to be more vulnerable to RowHammer, as existing mitigation mechanisms either do not scale to support chips of very high degrees of RowHammer vulnerability or have significantly high performance overheads. Thank you for your time and attention. I invite you to listen to our full talk and read our paper for more details.